Hi, I think you would agree if I say you cannot spoil a bad book with the good pictures, and it's probably true for scripts as well. With scripts, it is rare that it can be good without any illustrations. It is important in a sense that it helps you to understand your data and what to do with them. Previously, I wrote a script which I name edgeR Quick Start, which comes from edgeR tutorial Quick Start chapter. Briefly, you load edgeR, then get the data. Then you filter duplicated names, otherwise you cannot make row names. Then you define groups as they recommended in a brief format that simply directly columned in you replicate 1 7 times, 2 4 times. Why? Because that's how column names are divided between ages old and young. And then you declare DJ list as accounts are for data, and group is a group. And then you check samples. It's okay. Group 1 is age above 50, group 2 is age below 30. That's correct. Then we do filtering, which reduces the size of the genes because many of them are not expressed. Then we'll normalize and log transform. It goes in one line. Log transform is inside the normalization. Then, since we don't have any sample table, we can use only a group column for the design. Actually, in this case, you indicate samples. Otherwise, it will go into this line, not to the sample table. Then you do a fit, and then you check the names, group 1, group 2, then declare contrast matrix, QLF test, top tags. You have them, 127 genes found. It looks like script works well and we got the results, but doing it without illustrations carries a danger. We might miss an elephant in the room. Let's now do it again with the figures and see how it will change our opinion about this dataset. First, we load the libraries, stringR as well. We load the data exactly as it was, and then we remove duplicate row names exactly the same way, no changes. Now, instead of single line for a group, I would like to make sample table. That's more standard, more conventional way. We can make it out of column names. Column names indicate the source. The source is a human bone marrow, then age, then a gender, then a cell type, HPC. We can split all these column names by underscore. That's why I imported stringR. That's more stable, more useful string split function. There is another one. And then we generate a new column names because they were missing. And then we correct row names because they were spoiled during this splitting process. Then we remove age out of age. I can show you what is now. Yeah, not good, not yet. Using gsub, and then declare it as data frame, otherwise it will stay as matrix. And then we still have to add a group because we don't use ages as ages, we use only young and old groups. So first we declare everything as old, and then we declare ages which are under 30 young. And now sample list is complete, group old and young, with ages, with gender. The rest is not of much importance, it's the same. Now we declare edgeR list as it was, but we check the samples and we check that it all agrees, no mistakes. Now the first block of figures comes. First, it is a bit of formality to do a histogram and make sure that it's all like expected. There is kind of bell shape in the middle, and there are lots of zeros and low values at the beginning. That's nothing unusual. Then we do a box plot, where for colors we use as numeric as factor y samples group, which is old and young, and so we see immediately who is old, the red one, and young. And we notice that the last sample is a little bit down. Why? Because very likely it's not enough reads and genes in it. And we check it as we invented this plot before, and we see that by genes this number 11 is down, not by reads actually. And then we plot MDS, that's lemma. And if you are confused with these long names, which are simply first column over here, you can work on the shorter names in your sample, or you can simply say labels are 1 to 11. Then it's somewhat easier to read, and if you don't see it well, you can increase the font. Now you see it well, and you can also add the title, that's okay. Then the next chapter, filter, is all the same. We reduce the data size. We can actually check again and see that it's instead of 26,000 it's 14. Now we normalize and do a histogram of row sums just to check what we have. It's for every gene what's the sums of CPMs. It's counts per million now and logged. There is no other ways of extracting log norm data other than take CPMs which are available in a edgeR list and say log is true, and then you do a box plot of it. You see that they are not normalized, okay, only this sample leans still to the bottom, and we can repeat the plot and text, I don't like it. Now dots are smaller, filled red. Now it's easy to read the text above it. It's 11. You can also shift it a bit, but yeah, it's technical anyway. So sample 11 after normalization is even more outlier than it was. Now we do a fit, and after the fit we have a new illustration. When you do a QL fit, for this particular fit function you have a plot QL display. It's a new one. The X scale is still the same, it's a log 2 CPMs, it's always log transformed read counts, but here it's not standard deviation or variance, it's a quarter root mean deviance in the two forms, squeezed and raw. It is necessary for the calculation of significance. I hope it all works well. After this we can check the fit and groups, put it right way, old minus young, that's what we are mostly interested. Then we do the second round of test, now generating p-values over here, and then do top tags, and we select tops below 001, and then we see some table and the results. But also you remember there was a function decide tests, which does it for you, and pay attention that edgeR is quite lousy in all these stops. Let's check how this will work. It says nothing. These are more realistic results of the analysis. In RNA-seq study, edgeR plays a major role and p-values are secondary to edgeR. What's going on? Is an outlier make it difficult for us? I tried it and the result was exactly the same. What else can we do? Okay, we can do differently. We can put it other way around, gender plus group, and check whether gender will show us a difference. Now we go faster, and then we repeat a fit, and dispersion is the same, and matrix is not the same, not too fast. Now we say female minus male, minus. Test top tags. We can skip it and go straight to decide test, and then a summary, and now we see, oh yes, there is a difference between female and male, and plot MD. Now it shows nicely a difference. And then you can generate a top table through the found gene names in this result table, and then also select from TT by this filter and get the table. Of course, there are some genes like exist. It's an X chromosome famous gene, which is always different between male and female. But then you can ask, okay, what if we say only group over here? How this will work? We ignore the gender and work with group only. What will happen now? Then we do a fit. Now we gain group old and young over here. CoilF test, top tags, decide test, and summary. It's not a lot, but there is a difference now, and we can generate a table. There is no exist anymore, and there are some names which I cannot discuss right now. But then there is a question, how it is possible that depending how you do design with the same group with or without gender, you either have differential express genes or you don't. For this you have to go back to the samples table and look at it again with a fresh knowledge what's happening here. What's happening here is what I haven't seen before, that there is a cofounded effect of a gender and a group. When we have a young group, it's mostly female and only one male. And when we have an old group, we have mostly male. Out of 7 individuals, only 2 female and 5 male. And therefore, you have to learn new word, cofounded. A confounding variable is a factor other than the one being studied that is associated both with the disease and the factor, and so on. In other words, when you add gender to your equation, then you don't see any effect of the group anymore, because all the differences are assigned to the gender. But if you remove the gender, that all the differences are assigned to the group. In other words, the results are inconclusive. We find the differential express genes, But there is a uncertainty on this list. What is actually defined by the age remains unknown. The possible conclusion of this study is that whenever you read something in the high-ranking journals and see the data on gene expression, if you find some glitches in the data, do not complain, because it's not unusual. But then you do your analysis, you make your opinion, and then you come back to the paper and you either agree, disagree, or say it's not yet conclusive enough. And speaking about elephants in the room, in this story the biggest elephant appeared not in the figures, but in a sample table. You never know where you will find it next time.